Okay, good morning, students. I hope my voice is audible to all of you. Fine. So we last time we have seen some of the steps required for the pre-processing in the current form of the grammar, so that we can do the parsing with respect to the bottom-up parsing. So we started with the first parser, which is known by the name of LR0 parser here. So why zero? Because we are not taking certain actions, we are not taking decisions with respect to the current look ahead token here. And that is why we are considering zero look ahead tokens here. So we started up, we ended up in this example where we introduced first the augmented form of the grammar, in which we have introduced the new start symbol of the grammar, which is S prime, by introducing this new production, which is saying S prime is deriving S. And this will ensure that always my parser will go into the accept state with this production rule here only. And then, sorry, we have seen the construction of this go-to graph, which is nothing again but just a DFA, which where in each and every state is including certain set of LR0 items here. And while moving from one state to another state, we perform the go-to operation corresponding to these grammar symbols here. Right. So the whole thing which we have captured here, if you can link this thing, that bottom-up parser, this LR0 parser is nothing about just keep on shifting the input in the respective states. Like this has been shifted here, up to this point, up to this point, and this point. And then now at the state 4 and this state 6 and 5, I can decide now I am ready to reduce. Ready to reduce means I am ready to reduce by this non-terminal A. Similarly by here also A, and similarly by here also, and similarly as here also. That I am ready to reduce to the non-terminal S prime, where I should also consider this state as an accept state, right? Because this is my start symbol of the grammar here. While the other states are focusing on shifting the symbols, right? As long as I can. So it's only about keep on shifting till the last when your dot is somewhere at the extreme right hand side, then you do not have, and now you decide whether you want to reduce or not. Right? So this is the thing which is captured by your go-to graph here. Is everything clear up to this point, whatever we have discussed? Any questions up to this point? We saw the construction last time. Any questions, any doubt related to this? So fine. So now with this go-to graph, we'll construct the actual relevant thing, which is the LR0 parsing table. Like we constructed the LL1 parsing table. So similarly, we will construct here LR0 parsing table. Now, as I said earlier, that my LR0 parsing table is going to be indexed by two things. One is action and the another is go-to part here. And this time, instead of indexing with the grammar symbols like we did in the LL1 parsing table, we have the state symbols here. As you can see, 0 to 6, we have 7 states here. And this is the action. So action is going to be indexed by your terminal symbols. I mean, action is going to be indexed by your tokens. That is, I mean, in the grammar, A and B are these terminal symbols, including the dollar symbol, which indicates the end of the input stream. Right. So, I mean, consider this line as it is. I mean, this is the bifurcation. And whereas the go-to part is going to be indexed by the non-terminal symbols. Now, how will I read this? How will I capture this, I mean, particular thing while taking the parsing action? So it'll say at any point of time, if your top of the stacks is containing this state, then let's say state 0, and your lookahead pointer is pointing to the symbol A, then you should perform the shift operation and go to the state 3 here. So here S stands for shift and R stands for reduce here. So one more time, if my top of the stack is containing the state symbol 0 and my lookahead pointer is pointing to the A, so I should execute this action, which is S3, which means shift this symbol, I mean this lookahead symbol onto the stack and go to the state 3 here. This is what it indicates here. Like, I mean, how we fill this entry, if you can see on state 0, fine. So if I'm reading the A, I mean, performing the go-to operation on A, I'm moving to the state 3 here. So that means I just perform a shift operation on A and move to the state 3 here. So this is why we have written here S3 here. Similarly, on state 0, on B, you can see I am moving to the state 4. That means I have performed the shift operation here, right? That's why we have written S4. We did not perform any go-to operation on state 0 with respect to the dollar symbol, right? So that is why it will be completely an error entry, and right now it is a blank entry. Let me show you this. So blank cells, consider them as error entries. Similarly, this is for the action part. Again, with respect to the state 0, with respect to, let's say, S, this non-terminal symbol, I am moving to the state 1. Fine. So this time I did not perform, this particular shift operation. I just signed that 0 on 1, this is going to be, 0 on S, let me move to the state 1 here. Similarly, 0 on A, I am moving to the state 2 here. Fine. So this time I am not performing any shifting operation. So consider this is my input symbol, this is my top of the configuration. So both these are stack configuration this time. So that's why we are not performing any shifting on the input here. Similarly, with respect to the state 1, as you can see, state 1 is not performing any go-to action here. So we'll say that always we are going to reduce this thing with the S prime, which indicates that I'll read only this whenever my lookahead pointer is pointing to the dollar symbol. And here we'll say, come on, now accept this, completely stop this. So that is why 1 on dollar, we are writing it here is accept here. Fine, guys. Similarly, for state 2, as you can see, with respect to the, A, we are moving to this state 3 by performing the shifting operation with respect to A dot A here, right? Similarly, again, with respect to state 2 on B, we are doing a shift onto the state 4 here. Like you can see here, this thing. Fine. So again, with respect to this symbol, 2 on A, we are moving to the state 5 here. Now let's look at, similarly, you can verify for the 3. Let's look at some of the reduce entries corresponding to state 4, 5, and 6. So let's talk about this state right now, 4th. So you can see here, I am not performing any go-to operation because my dot is on the extreme right hand side. So that means what? That I am ready to reduce now this configuration with this particular symbol that is not. That means whenever I see that my top of the stack is including this configuration, that is B, I should immediately reduce this thing with the A here. That means we have written here that with respect to force state corresponding to the A, B, and dollar, always I'll reduce by rule number 3. That is, so that's why we have indexed these we have numbered these rules. So reduce by rule number 3, that is A is deriving B here. Fine, guys, is this thing understood? Blindly, whatever my lookout symbol doesn't matter. I'll blindly reduce with respect to all these lookout symbols. Similarly, with respect to the state 5, you can see the dot is on the extreme right hand side. Fine. So we'll say I'll simply reduce by the rule number 1 here with respect to all lookout symbols. Either my lookout symbol could be A, B, or dollar. So that's why we have written here reduce by rule number 1 on this. Similarly, with respect to the 6 also, 6th state also, reduce by rule number 2 here. So we'll call these items as complete LR0 items because we do not have nothing to see on the right hand side of the dot here. Fine, guys, hope you have understood how we have filled these entries with the shift and the reduce. Any doubt up to this point? Anything which you are not able to visualize up to this point?
Sir, can you explain the go-to part once again?
Yes. So what does go-to part here with respect to the non-terminal symbols? Let's assume right now I am considering this state 2 here. So on 2, so state number 2, I cannot perform the shift operation. Why? Because just on the immediate right of the dot, there is a non-terminal, right? So that is just go to state 5. I'm not performing any shifting because we are always supposed to shift the tokens, terminals on. So that is why 2 on state the tokens, terminals on the stack, not this guy, right? As we said earlier. So that is why 2 on state 2, I'm reading A and I'm moving to the state 5 here. Similarly, on state 3, let's take state 3 here. With respect to again this. So state 3, again, I am reading A and I am moving to the state 6. So again, another thing is not a terminal symbol, it is a non-terminal. So on state 3, this is my picture here. Is this thing clear now? Go to part?
Yes, sir.
So in the third state, how did we get A gives dot A and non-terminal A?
On the third state, which LR0 are you talking about? The first one, the second one. Fine. So the first LR0 item is A is deriving A dot A. So what should be my next step? I need to compute I am expecting certain derivations which are supposed to be derivable from this symbol, that is A. Now, what does this mean? That means I need to determine the closure. So I'll rewrite these productions. A is deriving A is deriving B as it is, keeping the left dot on the left hand side. This is exactly we discussed last time.
Okay, got it.
Fine. So this is closure we discussed last time. So this is the construction of the LR0 parsing table. And now, just like LL1 parsing table has helped us in parsing our current input, now this table is going to exactly doing the same thing, but in a different way, right? So let's do that now, because that is the main thing, that how this parser is going to perform the parsing. So we have this grammar and we have this table with us. And the blank entries, as I said, these are error entries, all right? And now let's do the parsing. So we considered this input right now, that is AABB, fine? And let's see how this parser will parse this input here, corresponding to the configuration of the parsing table. So what is the initial configuration of the input is AABB followed by this flag, that is dollar symbol. And what is the initial configuration of my stack here? So stack will be always, will be filled with my initial state, that is 0 here. So recall, in my LL1 case, always the stack is going to be filled with a dollar symbol, because there we do not have the concept of states. But here we have, and that's why the initial configuration will always be the states, the initial state 0. That means the top of the stack is 0. Now, how we should proceed? So we should proceed. My top of the stack is 0, and my lookat pointer is pointing to this first symbol A. So what should I do? I mean, the operation is in front of you. It says perform a shift operation and go to state 3 here. That means perform a shift operation means that push this lookat symbol onto the stack first and push this state or also on the stack also. That means go to the state 3 here. So this is exactly we did. Push A and state 3 onto the stack and increment your lookat pointer to the next particular symbol. Fine, guys, making sense? We just perform the shift operation, and this state symbol is capturing that what is the valid configuration below this, that is A here. So every grammar symbol is going to be indexed by state, as I said earlier also. Fine, guys. Proceeding further. So my top of the stack is now state 3, and my lookat pointer is pointing to the next A symbol. So what should I do? I should go back to my table and I'll say, again, perform the shift operation and go to state 3 here. So that means, again, I push this A here and the state 3 also onto the stack here, and I'll increment my lookat pointer to the next input symbol. And my configuration of the input will become like this. So my lookat pointer is pointing to the first P. Fine, guys. Similarly, my top of the stack is again now state 3, and my lookat pointer is pointing to the B here. So my top of the stack is 3 on B is saying perform a shift operation and go to state 4. That means push B onto the stack and state 4 onto the stack and increment your lookat pointer to the next P here. Fine, guys. Up to this, everything is clear. So shift says keep pushing onto the stack, the terminal symbols and also the corresponding state symbols. Now, my top of the stack is pointing to the state number 4, and my lookat pointer is pointing to the B here. So what is the action? So 4 on B, it says reduce by rule number 3. Fine. So now it is saying now you have reached somewhere at the end of the production. So 4 on B, reduce by rule number 3. Where is our rule number 3? This is our rule number 3. Now, what does it mean? That means I have to pop certain symbols from the stack and I'll push this guy onto the stack. Fine, guys. Now, the question here, how much symbols I have to pop here? So as of now, it clearly seems that, okay, since we are reducing by this, so that means we have to only pop this. But here we have the state symbol also. So that's why I said that every grammar symbol is going to be associated with one state symbol. That means if I have one grammar symbol on the right hand side, so I have to pop 2 symbols from the stack. If I have 2 symbols on the grammar and on the right hand side, that means I have to pop 4 symbols from the stack, because this could be indexed with one state and this could be indexed with another state here. So always remember that whatever is the length of your right hand side on which you are reducing, you have to pop twice the symbols from the right hand side. So that's why we said replace by A is deriving B and pop 2 symbols from the stack. That means these guys, fine, and push A onto the stack here. Fine, guys, this much is clear. And now, because A again has to be related to some state symbol, so where I should get, so I should again see right now my configuration on the stack is something like this. Let me rewrite. Fine. So I'll come here, I'll see now 3 on A. Look at this configuration. 3 on A is 6 here. So that means I have to push 6 onto the top of the stack here, and that's why we exactly did this.
Sir, Could you once again explain how did we decide the state, like what state we have to push?
Yes. So your current configuration was this one after pushing A. So 3 on A. I mean, this is the thing. 3 state number is 3, and this is my grammar symbol. So I just looked into the parse table. 3 on A is intersecting with this go-to symbol, that is 6 here. So that's why we pushed 6 onto the top of the stack.
Okay, thank you, sir.
This is the significance of the go-to operation with respect to the non-terminal symbol. So that's why we said we did not perform any shift operation, did we? 3 on it. We just pushed the symbol, state symbol on the top of the stack. Fine, guys, up to this point. Now, let's move further. My top of the stack is 6, and my look at pointer is pointing to the B. So what should I do? 6 on B reduced by rule number 2. Where is my rule number 2? This is my rule number 2 here. So that means I have to reduce this thing with this thing. That means this symbol will be indexed by state, and this symbol will also be indexed by the state. And as you can see, 3 and 6 are the state numbers. So that means 2 is the length of the right hand side. So I have to pop 4 symbols from the stack configuration. That means this, and this will simply wash away. Fine, guys. So my configuration will become right now 0A3. And what I'll push the left hand side, which is this here. And again, I need to assign some state symbol to it, right? So I'll see 3 on A is again giving me the corresponding thing, that is 6 here. So that is why we have written 6 here. Just similar process which we did earlier. And here, remember, my look ahead pointer did not change. It is still after reduction. While reducing, my look ahead pointer is not changing. So again, my current configuration on the top of the stack is 6, and my look ahead pointer is pointing to the B. So 6 on B, again reduced by rule number 2 one more time. So that means, again, I have to pop 4 symbols from the stack here, right? So my configuration will become only 0, and I'll push A onto the top of the stack. Fine, but I need to associate some symbol with this because this is the initial state. This can't be related to any grammar symbol. So 0 on A, you can see from here, 0 on A is 2. So that is why this is our current configuration on the top of the stack, that is 2. So 2 on B, again you can see, so this time again we are performing the shift operation. So now shift operation says simply push the B and go to the state 4. That means push 4 on the stack here. And my look ahead pointer is now pointing to the next symbol, which is dollar here. And 4 on dollar, as you can see here, 4 on dollar is reduced by rule number 3. That means this thing. So pop 2 symbols, right? So configuration would become 0A2A because we have push A onto the stack here, and 2 on A will give me 5 here. So that means this is the state symbol which is associated with A here. And now 5 on dollar, as you can see, 5 on dollar is saying simply R1. So R1 is my this thing. S is deriving AA here. Fine. So that means I have to pop 4 symbols first, and I'll push the S. Let me write here 0S on the top of the stack here. And I have to also associate one symbol here. So 0 on S, you can see, is 1. So this is my configuration. Now 1 on dollar, as you can see, is completely accept. This is where I should stop here. Now remember, in LL1 parsing, our stack becomes empty, but here it doesn't. This is my final configuration. 1 on dollar, let's accept it. And see, we have also constructed the parse tree while reducing. So whenever I was reducing, like first time my configuration was this, right? So first time I reduce by this particular thing. So I must say my tree was something like this. So this is, I mean, this is somehow capturing like this. A is deriving B. I mean, when I first performed the reduction with this rule, and then later on I perform the reduction by this A and A. So like whenever you are performing the reductions, so your tree construction will happen subsequently. Fine, guys. Any question, anything up to this point? So this is the way how one should process. I mean, sorry, how one should parse with respect to this first parser, bottom-up parser, that is LR0. So what are the steps as we go along? I mean, go back. First, augment the grammar, introduce the new start symbol, construct the go-to graph, construct the table, and if you have been given the input, just parse it with this configuration. Fine. So this is the thing that one needs to understand. I mean, while construction of the parse table and with the I mean, with respect to the related process of the parsing here. So here you can see with respect to each and every state symbol and with respect to the lookat pointer, always we are performing the unique operations. Either I am performing shift or reduce. I did not get any conflicting operations. I did not get any multiple defined entries. Multiple defined entries, let's say 0 on A, am I also performing some sort of a reduction? No, I am not, right? So each and every state corresponding to the grammar symbol is indexed with only unique entry, either shift or reduce. Fine, guys, any question up to this point? Otherwise, then I'll ask you questions certain now. Then. Fine, guys. So this is the overall process of the first bottom-up parser. Now let's discuss few important things. So here, what thing is coming that we have a large category of the type 2 grammar. We already know what LL1 grammar is out of the context-free grammar. Now we should also know which grammar is LR0 grammar. If you have been given the CFG, so you say that a grammar is LR0 if its LR0 parsing table does not contain multiple defined entries with respect to the shift or reduce. Making sense, guys, as of now? Or you can also dictate the same point that any CFG grammar is LR0 if it does not have any shift reduce or reduce conflicts in any of its states. Both the terms are valid. Then I'll say my grammar with the given CFG which you have given to me is LR0. Easy to digest this thing as of now. So let us see, I mean, what this thing is. So first, what we'll do, we'll try to understand the algorithm now because we have already seen the example, and then we'll pick some few examples so things would be very much clear to you. So possible actions in the LR parser, what we have done till now. So let's assume that my top of the stack is including the state symbol, SI. Fine, this is my state. And my current lookat symbol is AI. And what are my actions here? So it says action will take only 4 values. So corresponding to any state symbol and the current lookat pointer, like we did. So like shift, reduce, accept, or simply throw an error, right? These are the 4 values. So one possible action could be this shift and move to the state J, right? So shift AI onto the stack here, right? I mean, because this is my current symbol, and go to state J. That means push J as well. Otherwise, my action could be reduced by rule number K. So reduce by the production rule number K here. Or it will simply say accept, or it will simply throw an syntactical error. Fine, guys, this is what we have seen till now. Now, contents of the parser here. I mean, what is the stack configuration at a certain point of time? So it says that the following tuple is going to define the configuration of your LR parser at any point of time. Stack contents and the remaining input. And this will completely become your guys the concatenation, because this is where your dot is coming, right? Just try to visualize the remaining input which is supposed to be parsed, and this is my rest of the configuration of the stack. So initially the configuration is the initial state on the top of the stack, and this is my complete input which I am supposed to parse, followed by this dollar symbol, right? And what should be my final configuration, where I should accept? So that is your final configuration. I mean, just try to recall that example. Always I have the initial state, always I have some grammar symbol x1, and which is related to some state symbol, and this is the rest of the input, that is dollar. So you just recall, I mean, the previous example. This is how we start: initial state 0, any grammar symbol s, and the state symbol which is associated with s, and on dollar here. So that is why we are saying that always our final configuration is something looking like this. Don't think that your stack is going to be empty this time. Fine, students? We are just trying to formalize things with the help of that example. So again, let's try to relook what exactly we have seen through some generalized notion. So suppose if your stack configuration is something like this: initial state corresponding, I mean, this grammar symbol, and this is the corresponding state. And again, these, I mean, every state symbol is corresponding to some grammar symbol here, up to this state SM here. And this is my input here, which I'm supposed to parse. So it says if action of any state corresponding to AI, I mean, SM, because my top of the stack is now SM, and this is my lookahead pointer AI. So if this is the thing, shift, that is S here, that means the configuration will become something like this. So I'll push AI on the top of the stack, and I'll go to the state S here. That means I'll push the state S onto the top of the stack here. And my rest of the input will look like this. So my lookahead will pointer will point to AI plus 1. Fine, guys? On the other hand, if my action corresponding to state and corresponding to this lookahead symbol is reduced by this rule, I mean, earlier we write reduced by rule number, so this time reduced by the corresponding rule, then it says that where consider that length of beta is R here. So I'll delete R symbols from the top of the stack. So that's why we are written here X sub M minus R, S sub M minus R. And we pushed A first and the corresponding S symbol. So this S symbol will extract from goto of S M minus R comma A, right? Which is exactly. So just try to visualize, we did exactly the same thing in that example. And my lookahead pointer will not change. I mean, in that case. So my lookahead pointer will point to the same thing. I mean, this is coming from here. Fine, guys, nothing has changed. We are just formalizing the things. What are the other possibilities? So again, this is the configuration. I mean, suppose, so if S of M and AI is equal to XF, then my say parsing is completed, immediately stop here. And if my action corresponding to certain state symbol and corresponding to lookahead symbol is saying error or an empty cell, then simply throw an error or error recovery routine here. Fine, guys. So let's see lastly now what exactly we have done in the LR parsing algorithm. I mean, exactly the same thing. So initially my stack is indexed with the initial state S0, and my input is completely W followed by dollar symbol, right? And I'll just enter into the infinite loop as long as I can consume the inputs from here, and the input symbol. It says if action corresponding to this state S and look at pointer is shift to the state S prime, then what should I do? I should push the current look at pointer, push that state S prime and increment your look at pointer. This is exactly 3 operations I have to do, which we did in that example as well. Else, if my action corresponding to again state symbol and corresponding to that look at pointer is reduced by the corresponding rule, A is deriving beta. So in that case, pop twice beta symbols, 2 times beta symbols from the stack configuration, push A and compute the goto of S double prime comma A. S double prime would be the any state which is on the top of the stack here, right? Just below on the top of the stack. So we have mentioned that S double prime is a state at the top of the stack after popping 2 times beta symbols. Otherwise, if my action is accept, then I should immediately stop or simply exit. Otherwise, I'll simply throw an error. Fine, guys, is anything we did differently from our example which we haven't shown in this algorithm? Just let us know so we can discuss. Fine, guys, any questions? Fine. So now, this is one more example corresponding to this grammar. So you need to construct the LR0 parsing table through the construction of goto and all, and just see whether you can parse this input or not. Fine. And this is a valid input, assume. Fine, guys. And the form of the grammar is not important here. As you can see, this grammar is suffering from left recursion. Still, bottom-up parser says, my goal is not to look at the common symbols at the first or its left. My goal is to just keep on continuously shifting the input to the end, and then I'll decide whether I'll reduce or not. Fine. So just try it. I have to come to some other things. Now, as I said earlier, now your form of the grammar would be LR0 if your parse table is not containing multiple defined entries here. Can we decide whether this grammar is LR0 or not? Come on, guys. LR0 or not? How we should prove it? Come on, guys. I need certain interactions from your side. We already discussed this thing. We have one grammar, and the question has been asked to you whether it is LR0 or not. What does it mean? How will we prove it? No answers yet. Come on, guys. Please be interactive here.
Sir, will we have to make the parsing table?
We have to construct the parsing table, and we'll see if any of the entry is containing some multiple defined entry. Then I'll immediately say it is not a LR0 grammar here, because give me any input string, I cannot able to parse it because I have multiple defined entries in my parse table. So this grammar is obviously not LR0. And hence we'll say that we have some parser which is somehow less powerful parser to parse that particular input here. So first, what we'll do with respect to this example, we'll immediately come up with the augmented form of the grammar in which we have introduced this new production with the new start symbol of the grammar, that is E prime. Fine, the first step. So this is my new grammar with respect to these numbering so that I can denote when to reduce by the corresponding rule number. And this is my go-to graph here. Now, as I can see, there is no even need to construct the parse table, right? So long. One can easily decide whether it is LR0 or not. As you can see, now you know how to construct this, right? So I started with E prime is deriving dot E. Then again, I have to introduce all the productions of the E, considering dot on the immediate left-hand side. And again, I have to include all the productions of the T. So including all these productions on this particular thing here. Fine. So now here, as you can see in this state, corresponding state number 2 here, I have one complete LR0 item where dot is on the extreme right hand side, right? And I have another LR0 item which is performing a shift operation. Now, what does it mean? It means something that corresponding to the state number 2 and corresponding to, let's say, symbols plus and ID and dollar, I may get certain conflicts. Let's see how. So I'll say corresponding to this plus, 2 on plus will go to state number 4 here, right? So 2 on plus goes to the state number 4. So that means, let me write here shift and I'm moving to the state 4. But when I see this production on state 2, that means I have to reduce corresponding to the rule number 2. That is E is deriving T here. Then what should I write? I should write reduce by rule number 2, reduce by rule number 2, reduce by rule number 2. Fine. And now I am getting the multiple defined entries. I don't know whether I should go for shift or I should go for reduction. Whenever my top of the stack is 2 and my look at pointer is pointing to the plus. So I am getting a conflict. How should I parse this? So this is a less powerful parser, and this is the construction of the complete parsing table. So I do not have to construct the whole table. I do not need to construct the full go-to graph also. Whenever I am stuck in such situations, so I can immediately sense that I'll get some shift reduce conflict. Fine, guys. So I'll say that obviously this form of the grammar is not LR0 because I am getting multiple defined entries. And hence, I'll say still I have constructed one parser, and I should say this is a less powerful parser because it is coming across some shift reduce conflicts for some form of the grammar, which is not LR0, obviously. Hope this is clear to all of you guys, how someone can detect whether your grammar is LR0 or not. Fine, guys. Any questions, anything up to this point?
So we can say this directly by seeing the common prefix, like T dot.
Right. We can say by the common prefix as well.
So in fourth state, the second and third line, they also
Fourth state, second and third line. There, yes.
So like before dot, we don't consider it blank as a common prefix, right?
Are you there? I mean,
Yes, I am there.
what is your question now? I mean, did you ask your question or is this clarification?
Never mind, sir. I got it. Yeah. I just
Fine. Okay. So guys, this was the scenario where one can sense whether your grammar is LR0 or not, because parser says that I cannot parse the given input because it is quite possible that I can stuck in such states, in such situations, like I shown you here. Fine. So this is one way to confirm whether your grammar is LR0 or not. Now, the question arises here that what was the, so I have mentioned the reason here. So the question arises here, but what is the exact problem here? I mean, why this parser is less powerful? Why it is not feasible for him to take some unique actions, when to shift or when to reduce? You see, right now, what we are saying, suppose there is one form of the production is like this. I mean, this is one complete LR0 item. And we are saying that we have consumed all this on the top of the stack, and assuming we have the stack symbol also. And LR0 parser says that doesn't matter what the look at pointer is pointing to the current symbol. I will always reduce this guy with this, that is E here. This is what LR0 parser says, and which we are saying that doesn't matter whether it could be B, it could be C, or it could be even dollar as any symbol. It doesn't matter to me, LR0 pass. I'll always do the blind reductions. So does it make sense? You see, there is one proper rule which should follow by this. I mean, which should be followed by your powerful parser, which eventually LR0 is not. If you are consuming this whole thing, right? That means it says that perform the reduction with E only when the current lookahead pointer is pointing to that symbol which is follow of the left hand side. Just try to visualize. If my follow of E is not that symbol on which lookahead pointer is pointing to, I should not reduce. Making sense, guys? Yes or no on this? Because this is already consumed, this is already finished. Now, what E is, I mean, what symbol is following E, that obviously will come in follow of E. And if that symbol is not in follow of, suppose follow of E is equivalent to A, then this is a valid reduction. If follow of A is not including B and suppose here it is B, then I should not do this reduction. I should do some other thing. I should do the shifting and all. Making sense, guys? Did you understand this justification? Why is it not powerful? Because it is doing some blind reductions. That is why, I mean, it makes more sense why this 0 is happening here. It doesn't look at the lookahead symbol and it performing the blind reductions here. But the actual reductions should happen with this rule. That whatever the symbols which are in follow of left hand side, if those symbols are your lookahead pointer, then only you should go for the reductions. Fine. So here, let us try to, so we are moving towards the next parser, which is SLR parser, and whose name is denoted by the simple LR parser, which overcomes the disadvantages of the LR0 parser. So it is completely similar to LR0 parser, except one small change, which I have just tell you, that except that reduce entry, that LR0 always focuses on blind reductions. The reduced productions are written only in the follow of the variable whose productions is reduced. So only one small change. SLR parser says, oh, come on, I will augment the grammar, I will construct the go-to graph same as it is, and I'll construct my parse table in the same way, except one small modification. I will not do the blind reductions. I will do the reductions only under those terminal symbols on which the follow of left hand side is giving me those terminals. Fine, guys. So let us see quickly the algorithm for it. So I mean the same algorithm, construct the items, perform the shift operation corresponding to these items, and just a small change that whenever your production is this, I mean, your LR0 item is this, A is deriving alpha dot. Then your action corresponding to certain state and corresponding to certain input symbol reduce by this production only if your A is coming in follow of A. This is the only thing. Other things are completely same, except with the same production, and go-to also is the same for that. And all the blank entries would be errors here. I mean, if I construct the SLR1 parsing here, right? So same go-to graph, this time I have kept it in red color, I mean green color. Now it is at safer side. And I am going to construct the SLR1 parsing table. And SLR1 parsing table says, with respect to state 2, because I have one complete item here, so I'll compute the follow of E first. What is follow of E here? So if you look at the grammar, follow of E is nothing but again follow of E, and follow of E is nothing but follow of E prime. And follow of E prime is nothing but, because this is the start symbol, that is $. And that is why you can see under state 2, corresponding to the $, symbol, we are reducing by rule number 2 here. That is E is deriving T here. Fine. Whereas corresponding to this plus, so 2 on plus is going to state 4 after performing the shift operation. So we did not reduce by ID, we did not reduce by plus here. Fine. Similarly, with respect to the third, state where we have one complete item. So we are not writing the blind reduce entries in the state 3 corresponding to plus ID. We'll first compute follow of t. So what is follow of t? Follow of t is one is plus and follow of t is follow of e, and follow of e is nothing but dollar here, right? So one is plus and the another one is dollar. So that means I will write these reduce entries under these columns, plus entry. Now what does it mean? It means at any point of time, if my top of the stack is 3 and my look ahead pointer is pointing to plus, then only I should perform the reduction with the rule number 3. And let's suppose if my look ahead pointer is pointing to ID, then I should not do the reductions. This is what SLR parser says. Is this thing clear, guys? Similarly, with respect to state number 5 also. So follow of E again is dollar here, right? So that's why we have written the rule number 1 only under the dollar sign here. Any questions, guys, up to this point? So now, on what basis I'll say that my grammar is SLR1? Come on, guys, this is my question. On what basis I'll say my grammar is SLR1? Come on, guys, please interact. Give me some answers. Doesn't matter whether it is relevant or irrelevant. I'm not asking you anything which we haven't discussed yet. I'm asking you a very simple question that right now we did not, I mean, this grammar is SLR1, or I can give you any other grammar, and if I'll ask you whether it is SLR1 or not, what will you do? I mean,
Sir,
how will you respond?
It is SLR1 if there are no multiple entries in the parsing table.
Correct, absolutely correct. So I have to again construct the go-to graph, fine. And if I find that if I am again coming across multiple defined entries, because again it is quite possible that just because I have introduced this new rule, it is not at all necessary that I may not hit any other conflict. I may hit. If I am hitting any conflict, then again I'll say it is not SLR1. Because, and why it is 1 now? Because now I am taking the action with respect to the look ahead pointer, guys. This is very important thing, right? Why SLR1 is called SLR1? I mean, most frequently asked your questions in your, I must say, in campus interviews, and why LR0 is called so LR0. So here we are taking the decision by looking at the current look ahead pointer, and there we are doing the blind reductions. We are not looking the current look ahead pointer. Fine, guys. So again, blank cells are error entries. So today, guys, we discussed the construction of the LR0 parsing table and the construction of the SLR1 parsing table. And if both these tables are not coming across some multiple defined entries, so we'll say the current form of the grammar is either LR0 or SLR1. Fine. And if they are not, then obviously they will hit the multiple defined entries. I mean, you have to identify such states quickly. Fine, guys. Let's stop here for today. Any questions up to this point? So the course content for your quiz 1 is up to this lecture. That is up to the SLR1 grammar here. So I'm stopping here, guys. Any questions up to this point? I have also uploaded few practice problems with respect to both these grammars here. Yes, guys. Any questions?